Hello everyone, how are you doing? So first of all, thanks a lot for loving my NLP video series. And in the continuation of NLP video series, I'm gonna also continue more NLP videos, and those videos will be based on the BERT. So the many of you had requested me to make a video on the BERT. So this is the time to get started with the BERT. So the first of all, we will take the introduction of a BERT, and after the introduction, then from a next video we will start the coding on the BERT. So we'll be using their Keras and some other the NLP libraries along with the RNN, LSTMs, and of course the TensorFlow. Alright, so let's go ahead, get started with the BERT without wasting time. And first of all, one more thing I should tell you that this is not my presentation. I have taken this presentation directly from the internet to explain you. I have found that this presentation is really good, and I thought that why should I waste my time to make my own presentation? Instead of, I can get started with this presentation with the due credit to these speakers, Yao Feng and CEO, there is advisors, and this presentation was made on this date and blah blah, all those things. So once again, all the credit goes to these presenters, and of course, I think this is the organization NACLHLT. Alright, so I'll be also dropping the link of this presentation in the video description. If you want, you can also download this presentation from the internet. Alright, so let's go ahead, get started with this presentation. So this presentation have actually the 5 modules. In those 5 modules, it first talk about the introduction, then the related works, and then finally how these BERTs are being done, and then finally the experiments, and then the conclusion. The one more thing you see there, the BERT is deep bidirectional transformers for the language understanding. So I'll tell you what is the full form of the BERT. A BERT is bidirectional encoder representation from the transformers. Now you see there it says that this is the bidirectional. That means it looks the forward as well as the backward. Then it encodes the language first, and then it also learns from the transformer. So I'll explain these things in this lesson, and then it do this language modeling. So let's go ahead first understand what are these language modeling. For example, if I ask you to predict this some word from a given corpus, so you will get something like this. Get the word, or you can say the probability of the prediction for a word T, WT, on the given W1, W2 or the remaining words, you can say till the WT minus 1. So it says that we are going to predict the WT words at the T instance by keeping the information before the T, that's mean W1 to WT minus 1. Alright, and this BERT is available in pre-trained language model form. That means you don't need to retrain whole this BERT model. So it is already pre-trained model is available there. You can download it and get started working on this model. And if you are absolute beginner for the NLP, stay tuned with this channel. I'll start the BERT NLP lesson from the next video. Alright, so let's go ahead and get started with the related work. In the related work, we already have a few models which has worked on the path of this BERT language. Although the BERT is advanced version of all those models which are already available before the BERT. So there were 2 pre-trained language model available, like a feature-based model which was the ELMO, and there you see this ELMO. ELMO is kind of the pseudo bidirectional model. A pseudo bidirectional model, if I say that, it takes these inputs, let's say these are the complete sentence and these E1, E2 is the word of those sentences. Then it first feeds in the forward and then in the backward. So this is not a complete bidirectional, but it is just pseudo bidirectional. And then finally this forward and the backward information of the words are concatenated together to get the final information, but this is not close to actual bidirectional model. There we have the another model, OpenAI GPT. So this OpenAI GPT model only takes the information before the words of that particular words. Let's say if we talk about predicting this en word, then it takes the context of all the words which has came before this en. That's mean it doesn't get the context of after this en. So that is what the problem this BERT has solved. So BERT has combined all these information in such a way that it can take the information from the forwards as well as from the backwards. So let's say if I want to predict a word E2, then it takes the context information before a E2 as well as after a E2. So all these context before and the after has combined together, or you can say the encoded together to predict the this particular words. All right, perfect. And this bidirectional encoder representation have these two forms. There is masked language model and next sentence prediction model. All right, so we'll discuss this. Let's say in the masked language model, we will discuss it later. So let's just remember that we have these two more language modeling there, MLM and NSP. All right. So, but before that, let's go ahead and see how this transformer works. Again, see there. So there we have discussed about the bidirectional. All right. So encoder is a normal form of the encoding. That's mean these words are encoded there. And then let's go ahead and understand the representation of from the transformers. So how this transformer works? There are many type of the transformers. Like earlier we had the sequence to sequence transformers. But in the sequence to sequence transformers, what happens? The language or these sentences are fed into the model word by word. All right. And these only have the information of the previous context, not the forward context. And then there is the encoder and then there is the decoder. So the information is encoded here in this layer and then finally it is passed to the decoder. The another thing also you should notice here that if I calculate the information for this word, then the information from the previous word, the mostly it is lost to if the sequence is large. All right, and then there is the decoder. So how it works? There is a given language and then there is the translation of this language. So this is the sequence to sequence transformation. So there is the one language, let's say this is the French language, and then finally it is translating this language in the form of the English language. All right, perfect. So there this encoder and the decoder is given in the form of here black box. So it takes there this French language and then finally it gives this English translation that I am a student. All right. Then there is the encoder and the decoder. All right. So let's say this is the encoder and the decoder for the, let's say this is the combination of this encoder and the decoder. So that is represented as the one black box here. Then there is the multiple encoder and the decoder in the parallelly actually. All right. To let's say there is just 6 cascaded layers are there in the transformers. There it is actually describing this paper. Attention is all you need. This paper is published in 2017. So this paper has this cascaded encoder and the decoder blocks. All right. So from the same paper, it the mostly here. There is encoder and the decoder. There is the new term has just came here. That's the attention. So the attention is term. This is particularly put the attention on those particular words which are most important in a particular sentence. All right. So that's the self attention there, and the self attention model is given here. So it takes these 3 input vectors there, Q, K, and the V. And these vectors are, there are a lot of the complex mathematical operations are going on here. And then finally it produces the output. All right. So let's say these are the X are the encoded input vectors there. And then WK, these are the feature vectors there. and then these are the multiplied together, then it produces there the Q matrix. That's the query. To match the others, there is the key which will be matched here, and this V is the information to be extracted. Then what happens at the final output layer, this Q and the transpose of this K is multiplied together, and then under square is their square root is actually the dk there, and then it finally got multiplied with the information to be the extracted matrix. Then it finally produces this final output matrix, which is a label actually, or you can say if it is classification or if it is sequence to sequence, then this is the final result. Alright, so these are the quite a complex mathematics, so I'm gonna skip these mathematics, otherwise this presentation will be really very boring. Alright, the one more thing here, so you see there the self attention, but there is a multi-head attention. In the multi-head attention, what happens, there is the layers, cascaded layers together. So there is just a single layer, but here these layers are cascaded together. That is actually multi-head attention. That means the information from a sentence can be fed together. That means all the words can be fed together. So that was the problem which we have been facing earlier in a normal sequence to sequence model. So there one word is fed at one time there. Alright, so that was the problem there. So with this multi-head attention, all the words in that particular sentence are fed together. So in that, all the contexts are available together. And then these complex mathematics operations as described here being happen for each of these the attention layers, and then final these results are being calculated. Then with this W0, which is actually multiplying these Z1, Z2 and all these cascaded layers together to get this final results. Alright, so there is the transformer. At the time of the 2017, attention is all you need was really very famous paper and very famous algorithm. Alright, so now this is, you have got this complete transformer. This is complete transformer working algorithms kind of things. So there is the input there, and then there is the output. So during the first, you need to train before predicting. So of course in the training, in the testing, you give input, you predict the output. But during the training, you of course give input as well as the output there. Alright, so there is the positional encoding. Do remember, this is attention is all you need. This is not a BERT, but these things will be used in the BERT. I'll explain the BERT later. But before explaining the BERT, you need to have some background idea how and why it is happening there. So there you have add to norm, multi-head attentions, feed forward, and addition and the normalization, all those things. Then it is finally faded here and then here. Then with the softmax, you get the final output. So the moreover, you can see that this is the block diagram, because nowadays we have a lot of the APIs available. So we actually don't need to implement these algorithms from the scratch. If you are beginner to the NLP or data science, you can just understand it just roughly. You don't need to get all the mathematics. All right, perfect. Now let's go ahead and understand what is the BERT. BERT is the bidirectional encoder representation from the transformers. We have already understand what are the transformers. We understand the definition of the bidirectional encoders. All right. So now you notice here that we have this model which is actually encoding your input, and then there we have the decoders, and the information is being fed here, and then final output layers are there. All right, so the four things, those things are happening here. So it has their input, and you can say these are the length and the height kind of things. That's mean there are the multiple, these layers are there are multiple layers are there cascaded together. All right, then we have there the multi-head attention there as well, and these multi-head attention, a cascaded attention layer, you can take it as A. So this whole multi-head attention, you can take it as A, and then there is H, height, and then there is length. All right. So in the BERT have the two model. One is a base model and the one is the large model. In the base model, it has only 110 million parameters, and in the large model, it has total 340 million parameters. All right. So now let's go ahead and discuss about the methods, how these BERTs are being done. So the BERTs are actually having a two type of the model there. One model, we already have discussed these two types in the form of if we discuss size, but there is another two type if we discuss about the training and the testing. So in the training, it has the one pre-training. So before utilizing a BERT in your task or a project, so there these two things happen with the BERT. The first was pre-training, a rough pre-training for this BERT for a large data set. So this pre-training happens with the unlabeled data, or you can say that there is unsupervised pre-training. So in the unsupervised pre-training, we don't have the target output, so it is just sequence training to understand the language for whatever language you are training this BERT, like English or any other language. So there it has this NSP. Now do you remember that we had discussed this NSP earlier? That let me show you. We had discussed there NSP is next sentence prediction, and there were masked language model. All right. So there we have the NSP, next sequence prediction. So this C is actually very important. So this is a CLF, that's the classifier information. So during this training, you get the information which will get the multiplied with the other BERT. If you use it in the testing, then that get multiplied with the BERT vectors to get the final outputs. All right. And for the fine tuning, you get a small data set. In that small data set, you have the input and the target output, and at that you fine tune this BERT model, or you can say you tune or reutilize this pre-trained BERT model for your task. So there it has done on the squared data set, NER data set, and MNLI data set to fine tune and test it and get the accuracy of this BERT language modeling. So let's go ahead and understand how this BERT language modeling is done there. So this BERT language modeling, each word tokens have these three layers. Now do remember, tokens, words are made of tokens in this BERT language model. So let's say you have this sentence. These are the two sentences. My dog is cute, he likes play, and then there is ing sep. All right. So with this, what you understand that my dog is cute, this is one sentence, there is a separator, then he likes play, and there is ing. So why this ing and there is ampersand sign? Because this ing was not present in the vocabulary. I mean, playing was not present in the token vocabulary in this BERT language model. Because this token, this BERT language model have only 30,000 word tokens vocabulary. So these 30,000 word tokens are the most frequent occurring words and the most important words. So the playing is made of play and the ing. So it has just removed their ing as a different token, and then play was present in this 30,000 token vocabulary. All right. So the first it do the token embeddings. In the token embeddings, after that it do a segment embeddings and then positional embedding. So each of these word tokens are made of these three layers, or three layer of these tokens. All right. Perfect. So there you have here C token, E, and there is T. All right. So there you have these tokens. All right. Tokens, there is a separator and other things, and then finally you have a BERT language encoding model at the end of this. So there next sequence prediction and mask LM. All right. So mask language modeling. So once if you try to get the next sentence, then you use the NSP to predict the what is going to be next sentence on the given particular sentence. And if you want to predict a particular missing word, then you use their MLM. That's the mask language modeling. All right. So first let's go ahead and understand what is this MLM. MLM is mask language model. In the mask language model, let's say you have given this sentence. In this sentence, what happens? One word is masked. That means the information for that particular word is not given to this language. And then finally we ask to this model actually. Then finally we ask to this model that what will be the output. I mean, what is this sequence? What is this word actually? All right. So this is how this training happens for mask language modeling. So 80% times during the training, that word is masked there. That means the information for that particular word which is masked is not passed to the BERT model. And this 80% is actually divided before that, sorry for that, let me re-explain you these things. So this is not actually the 80%, this is actually the 15%. So the 15% of all words, 15% of all words are masked. All right. Now again, so the 15% of words are masked, but out of those 15%, 80% time, do remember, out of these 15%, 80% of the time, the word is completely masked. That means the information is not given to this BERT model. And 10% out of this 15%. All right. So the 10% random token is given. Let's say if we say that he likes playing. All right. So it might, if you want to mask, let's say the playing, so you pass there he likes the. All right, there is no information about the playing for the 80% time. For the 10% of the time, you replace that playing with the random words like the jumping, walking, eating, or anything, the H or whatever you want to put there. And then the 10% of the time, that doesn't change. That's mean the 10% of the time, a same model is passed there. I mean the same sentence is passed there without any change. All right. Now let's go ahead and understand what is the NSP. So the NSP is the next sentence prediction. In the next sentence predictions, you have given one sentence. This is the two sentence because there is a separator. That's mean you can, in normal language modeling in English, what we learn, separator is full stop there. All right. So you have there one sentence and there is another sentence 1 and the sentence 2, and then we ask what is gonna be next sentence from this BERT. All right, and let's go ahead and discuss this fine tuning. So earlier, now we have been discussing this pre-training. In fine tuning, once this pre-training is done, then we do this fine tuning with the labeled data. In those labeled data, we pass the sentences there, and then we have also given a final matching output there, or you can say the target labels. And then finally we train this BERT model to fine tune it. Let's say if you want to calculate the sentiment, then we can give the sentence there, and then finally we can make it learn it is positive sentiments or the negative sentiments. Otherwise, you can also do it for the document classification or a document category classification. All right. Now you have a single sentence tagging task there, W1, W2. There you have a BERT, linear CLS, linear, and class, all those things. All right. So earlier we had there a single sentence in the class. That means single sentence classification task. Now here we have a single sentence tagging task. In a single sentence tagging task, that means you have given a sentence there, and out of this sentence, now you need to tag each of these words to particular label. So this is, you can also say that this is kind of named entity recognition. So there we are gonna say that, okay, this type I is destination, and there this November is a time, and second is also a time. So this is kind of the tagging of those particular words. Now there, the third task we have here, a sentence pair classification task. In a sentence pair classification task, you have, let's say, these sentences, sentence 1 and the sentence 2. So these sentences are passed there, and then finally we get the output there. So it's like a natural language inference there, where we have multiple sentences, then we try to get the information from those those sentences. And fourth task which we can do with the NLP is question answer tasking. Let's say you have their question answer model there, you feed there the document and then the question, then it finally gives you the output from those documents, starting and the end of the tokens. For example, if you ask a question, what causes the precipitations to fall, then what you get the answer there is the answer gravity. The 17, S is start and end is 17. That's when it says that the 17 number of word is the answer for this particular question. So there you have this question, it says that again there is this answer, and then finally you have this question. So for this question you have within a cloud answer, and this within a cloud have word number from 77 to 79. All right, so there you have again the question answering task here, explained it in a better way. So there you have a multiple question fed there, Q1 and the Q2, and then multiple documents also fed there, Q1 and D1, D2 and the D3. So at the first stage it gets trained, and then it learns from the scratch, and then finally it starts giving you the output as we had seen the previously. All right, so in the experiments Google had, and along with the Google, after Google published this model, people had also people had utilized this model for their applications. So their Li-Meng BERT model is available in the PyTorch language, PyTorch backend there for the machine learning, which is actually used this package there, and now they are using it for the I think they are using it for the Hugging Face transformation. All right, perfect. So their pair to sentence, I think they doesn't give you the much information. Yes, so there I think we have some information, like there we have input single sentences. Now it is trying to get the class. All right, I think these are the same thing which we have already seen previously. All right, now this is the final conclusion. So these are the references for the paper, and once again I should tell you that this is not my presentation. So this presentation I have taken from the internet. I'll give this link in the video description. You can also download this presentation from the internet. All right, so thanks a lot for watching, and please do remember, if you want more videos, please do comment there, and if you have any doubt, please comment there as well. Bye bye, have a nice day.